The mathematical universe hypothesis was recently popularized by Max Tegmark in his book, Our Mathematical Universe. Stephen Wolfram's method is called the computational universe, in which he uses simple rules to compute an emergent system with familiar physics. These two physicists are closest to my own hypothesis, and I think they are really talking about the same thing. Tegmark doesn't offer a specific mathematical set to test, so I will give the physicists something to get their teeth into. A mathematical set I call Big I2, which I have partially implemented in a computer simulation reminiscent of Wolfram's project. So I'm going to explain how a mathematical set, with rules even simpler than Wolfram's, produces emergent effects such as gravity, dark energy, dark matter, 3 space dimensions, and an hour of time. It also explains why our universe should be considered typical. I'm suggesting the standard model of particle physics emerges one or more levels up from the picture I'm giving, so I'll ignore that for now. I'll start with the philosophy, then the mathematics, which seems like it couldn't be any other way. I make as few assumptions as possible throughout. It's going to seem painfully simple, so I'm big on Occam's razor here. Then finally, the more exciting bit really, the emergent physics, which seems to match our universe. So I've made some animations to explain things visually, and I'm going to go through things pretty quickly to keep this video short. So let's get into it. I start with 0 assumptions and use Occam's razor to develop a concept of nothing as the minimal state of nature. I will show that this minimal state includes a natural structure which matches our reality. Starting with 0 assumptions means we can't assume logic holds in all cases. If logic doesn't hold, then a statement can be true and false at the same time. And the negative statement can also be true, and so logic does hold. So the 2 options we are left with are 1. Logic holds, 2. Logic holds and logic doesn't hold. Note that there cannot be a circumstance where there is less than logic holds. Either way, logic holds in some region. I call this region Maths World, or the abstract plane, or the Platonic Realm. It is not clear what form objects in this place take. If numbers are in this place, then is all mathematics in this place? Does mathematics come as a result of logic? 1 plus 1 equals 2, etc. gives us the set of natural numbers from 1 to infinity. A very simple infinite set. In what sense does this set exist? Is the admission of the Platonic realm into some classification of existence more than nothing? If the Platonic realm comes from logic, it would be illogical for there to be less than this. So nothing can't be less than this. Nothing must be this. The Platonic realm is there, but it is abstract. There is nothing, as in no other reality separate from this abstract plane. This is the simplest nothing that conforms to logic. This is the minimal state of nature. Simple, yet it contains all of mathematics. It would not contain physics necessarily. It would be timeless, perfect in its simplicity and form. Laws are obeyed faultlessly by diktat of logic. So how do we go from a timeless abstract realm and bootstrap ourselves up to a real live world that changes over time? We can't add anything, but we do have access to any mathematical set that exists. These sets are timeless and do not change, but if time can emerge as part of the functioning of the set, then from the point of view of things in the set, there would be time which has emerged naturally. Of course, the set must be very simple, and not look like it has been crafted to deliberately produce our world. It would not be the intention of logic to make our world. Logic had no choice in the matter. It seems like there is a lot in this so-called nothing. It seems from another point of view that this could indeed be considered everything. Every possible logically consistent abstract object exists in this world. That is a lot. So from these 2 points of view, nothing and everything are 2 sides of the same coin. The mental leap is to consider that there is no go-to reality from here. It is not that one of these possibilities is chosen at random and made real. If you're in a mathematical set, it seems real to you. This is obviously hard to get to grips with, but that is it. That is why there is something rather than nothing. We're in maths world. This perspective on time may seem contradictory, so let's do an analogy with the movie Citizen Kane, a timeless classic. You don't have to have seen it, any movie will do. Citizen Kane, from the perspective outside the movie, does not change over time. It is the same movie now it was many years ago. It exists outside of time from the perspective of the viewer, who can start it, stop it, reverse it, and the ending is always the same. From the point of view of the character, Citizen Kane, he feels the passage of time. He is young and grows up and dies in a linear fashion, even if when we watch the movie, the order of events does not follow linear time, and we can start with him being an old man and then jump back in time to when he was young. The two perspectives are different, from being inside the movie as a character and outside the movie as a viewer, but there is no contradiction. This is the same as for a timeless multiverse, in which time is felt by beings inside the multiverse. Mathematics from first principles. Interactor sets. If maths isn't your strong suit, don't worry for now, I will visualize it for you in a moment. In abstract maths world, there exists little I, and there may be more of them. We don't know how many there are. There might even be none. The collection of these little i's is the big I. This collection is called a set. I'm just using I as it is the first letter of Interactor. I could have called it action sets and used the letter A. It doesn't matter what I call the things, because I'm going to tell you everything about the things anyway. If there are two things, I might call one little I and one little j. The things don't do anything I don't tell you. The things don't have any extra properties I don't tell you. They don't have a shape. I'm not going to set up a space or a time for them to exist in. They are like abstract numbers. The natural numbers would be little n in big N, where n could be 1 or 7, etc. There are some rules for n in n, like 1 plus 1 equals 2, and there are also some rules for I in big I. So let's look at these rules for a general interactor set. We're not getting specific yet. Just like n in n, these little I can have a value, a number, data. We haven't said what data yet. This is the general case. We're trying not to assume anything yet, so we'll call it D for data. This data set D could be very complicated, but to keep things simple, in this video it's always going to be, just like n in n, it's just a number. Okay, next. These things can interact with each other. We know in our universe some things interact with other things. Is this an assumption? Well, we're assuming we're in something like our universe. Obviously some things interact. Which things can interact? I call the things which can interact adjacent. It's like they're next to each other, connected. If they're not adjacent, they can't interact. This is a bit like 5 is next to 4 and 6, so 5 can interact with 4 and 6. This is the general case, so we can just say for now, there is a rule which says which things are adjacent, and get specific later. Okay, next, the actual rules for how the things interact. So we know if they're adjacent, they can interact. What do they actually do when they interact? In maths, when we do something, we often call it a function. The function is the nitty-gritty of the interaction. The other stuff is really just setup. So when we do the function, we know what the interaction has done. This is the general case, so we can specify what the actual functions will be later. These functions can be very complicated, but in this video, the function is always going to be the numbers swap. So if there are two things, they swap their numbers. The number for thing I is passed to thing j, and the number for thing j is passed to thing I. Nice and easy. Finally, there are also rules which must be obeyed because the things are in maths world. I'm not going to write down all those rules though. Essentially they have to abide by logic. So asterisks, This is why there is non-local transfer of information in quantum mechanics. Entanglement always preserves logic. That's why there's entanglement, because we're in maths world. Logic can travel faster than the speed of light. Logic is instantaneous. It doesn't need a natural interaction to be preserved. I don't think I've made too many assumptions. In fact, I expect many of you will be thinking, I haven't even done anything yet. I've made so few assumptions. So let's get more specific. We're going to cover 2 examples with computer animations. The first one is just to warm you up, so you can see how simple this really is. In our first super simple example, big I1, the members of the set can interact with one other member. Little I and little j in big I1. Little I is not equal to little j. D is a mapping from big I1 to the natural numbers. A subscript little I is only little j, the one other member it can interact with. Big F equals f of little I and little j. F of d little I and d little j maps to d little j and d little I. Here we have little I able to interact with another member little j, in which the interaction involves swapping information about the energy value in dataset D from one member to the other. As this second member can only interact with one member also, by symmetry, this must be the first member. So we have only 2 members in the set. After each time period, the members have swapped energies, and then they will swap them back again next time. Remember that logic can't choose one thing over another. It just has to do everything. So all the possible instantiations of big I1, with different starting conditions, exist in a superposition of states. There is no arrow of time in this set. A choice between forward and back in time is arbitrary. There is no direction which feels more forward, like how we perceive space. Here is an abstract object which could be our reality, the interactor set I really want to show you. Even if you're not familiar with maths notation, you have to admit it's pretty simple. Small enough to fit on a t-shirt. Occam's razor eat your heart out. I will take you through how this kind of set can give us something like this. Set big I2. Members can interact with 2 other members, but only one at a time. Little I, j and k in big I2. D is a mapping from big I2 to the natural numbers. A subscript little j is little I and little k. I have specified that little I is not adjacent to little k and vice versa. Little j is in between the other 2, as I want to keep things simple for now and avoid loops. Big I2 has more interactor functions than big I1. In big I1, a level 3 member can only interact at level 3. On the theme of all possible things happen, a level 3 energy member in big I2 can interact at level 3 or 2 or 1. Energy values just swap. If there is no member to the left, the set will create one, because according to the rules of the set, a member interacts with 2 members. So a member is interacted with, which has a random energy value for dataset D. In big I2, there is not so much an arrow of time. Time is like a wind, caused by the stochastic processes which, over time, build up larger and larger probabilities that things won't go back to how they were before. The broken vase is more unlikely to repair the longer it goes on that it is broken. It is certainly possible to go back to how things were. You just swap back the 2 energy levels you just swapped. And now things are exactly the same as they were 2 time periods ago. But if nothing has actually changed, how is time felt? It won't be. It will seem as if no time has passed. Only when things change is the passage of time felt. If you want to go back further in time, by essentially repeating more interactions in reverse order, that is certainly possible and will happen. However, this kind of thing could also be interpreted as still following the direction of the wind, but a cyclic repeating system has been set up instead of the time travel interpretation. When a pendulum swings, is it going back in time on the swing back? We tend to assume not. Let's briefly look at big I4 and big I6. Big I4 explicitly makes a 2-dimensional space, a flat plane, Big I6 explicitly makes a 3D space, so it is tempting to look here for something which matches the physics of our universe. But let's not get ahead of ourselves. This video is about the seemingly more boring set Big I2, which explicitly makes only a one-dimensional space. So how can it match our 3D universe? Physics emergent from Big I2. So let's start with warping. We know from general relativity that space-time warps. Why does it warp? Something to do with mass and energy? High energy members of Big I2 have more possible interactions. The lowest energy members, energy 1, can have as few as 2 possible interactions if their adjacent members are also energy 1. One possible interaction to the left and one to the right. A region of high energy members has a lot more interactions to contend with than a region with the minimum number of interactions. More interactions means more time periods occur, because a time period is simply before and after an interaction. So more time periods happen here than here. The busy regions have more information, a bit like a busy computer network. Things get slowed down by this density of information being transferred around the busy region. As we haven't defined a time dimension, and this is all an emergent system, the time periods can take different relative lengths. It's tempting to think the less busy regions can just wait a bit for the more busy regions to do all their extra time periods. Depending on how you think about it, either this waiting is the warping, or the waiting is an artifice of our human common sense view of time, which cannot be, as there is no external time that the members exist in, and so the time periods have to warp to different relative lengths. In regions with less time periods, the periods are relatively longer. This means you would feel a force pulling you towards the region with shorter time periods, as it is relatively quicker to go that way. Interactions towards the busy regions are happening more often. There is simply more space-time in this region. This warping is analogous with the space-time warp we call gravity. A higher density of interactions, or a higher density of information compared to a lower density region, forces a warp. If this really is why there is gravity, the warping fun does not stop there. What else causes differences in information density apart from high versus low energy? Entropy. Entropy is about information. For two states of a system with exactly the same energy, a higher entropy state needs more information to describe it. This example has low entropy. Everything is energy 1, except the member in the middle, which is an 8. This state is unstable. Like a tower of sand, it is likely to collapse to a pile of sand in the future. There are 20 possible interactions, so this is the amount of information we need to describe the system. If we go into the future, things get messy pretty quickly, so now we need 25 interactions to describe the system, so that is higher entropy, more information, even though the total energy is the same. The future has more entropy than the past. A region with high entropy relative to a region with low entropy will also cause a warp. Does this happen? Do we see this extra warp in our universe? So-called dark energy is the obvious candidate, which physicists have been calling the force which causes the expansion of the universe. As the entropy of our universe increases, the difference between high and low entropy regions increases, and the resultant warp is the expansion of the universe. The difference between the past and the future is warping spacetime. On a related matter, let's look at inflation, which is the period in the very early universe when the expansion was very quick. As we can see, in Big I2, in the early stages, new members are added with a random energy value, which requires zero information. The gradient between a super low entropy state with almost zero information and the future state of the system with higher entropy will be a very steep gradient in these early stages. New energy and new spacetime is added to the set at the edges, which has little to no impact on the time clock of members in the center. This is a period of rapid expansion without diluting the energy density of the set, as each new member has the same average energy. This is obviously different to the Big Bang model in which all energy is created at the beginning. If we run the clock back, energy would steadily be removed from the edges of the set, and eventually forming a singularity. This seems to affect the first law of thermodynamics, conservation of energy. However, the edge of the set does not fit the conditions of a closed system. Any local closed region of members will conserve energy, as the only interactions are swap interactions. Big I2 doesn't obviously have the capability to do anything more interesting than make a one-dimensional line of members which warps in two different ways. One warp due to energy density, aka gravity, and one warp due to entropy density, aka dark energy. Let's say the normal first dimension is the x-axis. The gravity warp is on the y-axis, and the dark energy warp is on the z-axis. These y and z-axis warps are so extreme in places as to be indistinguishable from the second and third dimensions of a 3D space. These extreme places are black holes in the case of the gravity warp, and so-called cosmic rips in the case of the dark energy warp. So this is how the simple Big I2 set can make seemingly 3D spaces. I say seemingly because the picture gets more complicated when we consider what happens when these warpings happen on these two new dimensions. Well, they will warp, and create two more dimensions, and then two more, and then two more, ad infinitum. Hence this set will create an infinite dimensional fractal structure. So really, there are infinite space dimensions, but it seems to an observer that there are only three, because an interaction can't directly affect a dimension 2 steps away. However, warping effects can still be felt across these boundaries. This means gravity and dark energy effects will be felt in our 3D universe from these infinite dimensions, even though we cannot directly interact with all the matter and energy in these infinite dimensions. This is why there is so-called dark matter, which is what physicists have been calling an extra force of gravity from matter we cannot see. It is unlikely we are in the first of these fractal copies of the multiverse, if there are infinity of them. So we should expect previous iterations of this fractal structure to show up in something like the cosmic microwave background, as if there was something before the Big Bang. This explains there seemingly being evidence for cyclic cosmology theories, which have the downside of implying a big crunch, when the current evidence is for a big cosmic rip. This simulation is not to scale or representing how things really work. It's a model I use to visualize dynamic dimensions and dark matter. When maximum energy level 3 members interact, they artificially warp into the same place, which leaves a gap. With no members near enough to interact with anymore, the member behaves like the first member and starts a new dimension in blue. This is an analogy for black holes and cosmic rips. Remember, this is all happening in a superposition of states, so every member has the potential to form dimensions dynamically. On the green dimension, again a row of maximum energy level 3 members does the same thing and artificially warps, dynamically creating a new dimension, which is 2 steps away from the red dimension. So from the red dimension's point of view, this would be dark matter. In this set, I played around with zero energy members. When next to other zero energy members, the one in the middle has no interactions possible, and so for a different reason to blue, it behaves as the first member, which must interact with 2 other members, and therefore starts the green dimension. A benefit of this fractal infinite dimensional pattern of spaces is that it means a type of multiverse like Big I2 is a highly likely 3D universe. There may be other ways of getting a 3D universe, but this one makes a lot of copies of itself. Infinite copies. The number of copies is represented here using this exponential sum to infinity. So if the others don't make as many copies as Big I2 does, it is so unlikely as to be next to impossible that we are in one of those other types of multiverse. This means we can focus on testing limited cases of interactor sets, which are like Big I 2. Note that all of this emergent behavior is not dependent on the dataset D, which I have set to the natural numbers somewhat arbitrarily. Changing the dataset would be an easy way to produce different multiverses, so we can experiment with options like the integers or complex numbers to see if any lead to the standard model of particle physics emerging. I'm not funded, so all support is very much appreciated through Subscribestar, Patreon, and PayPal. To get your own universe on a t-shirt, follow the links below. Subscribe for more content. If you haven't already, check out my video explaining consciousness.